Thanks everyone for coming to our tutorial, and I hope you had a nice lunch. My name is Erin Catto. I'm a programmer at Blizzard Entertainment. And so I want to talk about this, this picture a little bit, tell you a short story. So when I was a kid growing up, I really fell in love with mechanical systems. In particular, I really loved these mechanical Lego kits. And I collected them, and I built them, and I had a lot of fun with them. Later on, when I went to school, I studied mechanical engineering. And I learned that these kind of mechanical systems could be simulated on the computer. And I thought that was completely awesome. And I wanted to be involved with that. And then later on, I learned that, oh, people are now putting these kind of mechanical simulations into games, kind of combining the two things I love. And so I thought that was just amazing, and I knew that's what I wanted to do. So I've been working on game physics for a while now, and that kind of, as I went through all that, I came up to this topic of this talk, continuous collision. I think this is it's one of the most difficult problems to solve in game physics. And I think it's, in general, also one of the most difficult problems to solve in games, at least at an algorithmic level. So I started working on this problem, and I was just working on this for months and doing all kinds of research, trying everything, and I needed some inspiration. So fortunately, I had kept all these Lego kits. So when I go home from work, after working on this problem, I would pull out these old Lego kits, and I put them together. And it kind of reminded me of why I loved what I loved. And so I would bring these Lego kits, and I reassembled them, and I brought them into my office and kind of surrounded myself with these. And they provided me with a lot of inspiration. So I guess that's kind of my point, is that if you're working on a difficult problem, try to find something that inspires you. It certainly helped me. So I'm going to get started now. Let's dive in. So games are basically like fancy flip books. We draw discrete frames and then hook them together and create the illusion of motion. This works fine for things like rendering or for animation. But for things like game physics, things that happen in between these frames can be vitally important. There can be events that happen between the frames that can determine how the whole simulation plays out. So for example, here's a simple case of a ball bouncing on a thin plane. And the ball is shown there at the discrete time steps. And the trace is kind of what you would expect the ball to do if you had even more time steps. The problem with discrete simulation is we need that ball to actually overlap with the plane so that it can respond and have a collision. So if the ball doesn't actually touch the plane, it can't actually have a collision. And so instead, you get this nasty bug called tunneling, where your objects just mysteriously fall out of the world. And this is not really working in games. You can't have this. So let's talk about trying to come up with some solutions to this problem. Well, I could just say, well, I'm just going to make the floor thicker, then I don't have to worry about that. And maybe for some games this will work. Like if you're making Virtual Go, you can just make the board thicker. But for modern 3D games, they're created in Maya. They're made out of triangles, soups, and all these thin triangles all over there. And you don't want your level designers to have to worry about this problem. So let's push the problem back to the physics engine. OK, physics engine, you solve the problem. And of course, I can make the floor thicker, but the object could start moving faster, and then I have to make the floor thicker again, and it's a never-ending battle. So here's another technique which has come around recently, and it's called speculative contacts. And the way it works is we just march the ball along forward in time. And so say we arrive at t equals 6. What we do is take a tentative time step till t equals 7. And then we're going to try to see if anything bad happened in between those time steps. And here's how it works. So I just wrap a bounding box around the t equals 6 position and the t equals 7 position. And then I find, oh, that bounding box, that's intersecting with that ground plane there. So I better do something about that. And the idea is, let's try to apply some constraint to the ball back at t equals 6 to prevent it from falling through the floor. Now, the standard contact constraint basically says the relative velocity along the normal should be greater than or equal to 0. If I just applied that in this case back at t equals 6, the ball will hit basically an invisible plane. And obviously, we don't want that in the game. It's going to seem like the ball just hit something imaginary that's not even there. So instead, what we do is we adjust that standard contact constraint. And so over there on the picture, you can see I have the distance d of the ball at t equals 6 from the plane. So what I do is adjust that velocity constraint so that the relative velocity along the normal can be somewhat negative. So I'm going to allow that ball to have some downward velocity, which is the current distance divided by the time step delta t. So I'll allow it to fall just that much that it would hit the plane, but I'm going to prevent the velocity from being any more negative than that. And so what happens is that at the end of the time step, the ball just kisses the plane. This is great, so we prevented tunneling. But there's some interesting things that are happening now. First, we actually slowed down the ball before it hit the plane. Well, that's OK if the collision is inelastic. But if I want some restitution, I want the ball to bounce like I had in the figure earlier, well, it's actually not going to bounce as much because I stole away some of its velocity in order to stop it from hitting the plane. You could maybe work around that. There might be some solutions where you could buffer up the velocity or something like that. Another problem is, well, this is a dynamic versus static case. The floor is static. What if the floor was dynamic? What if the floor moved out of the way before the ball actually reached that plane at t equals 7? Well, then again, now you have a situation where it looks like that ball just hit something invisible, and that's called a ghost collision. And that's a more difficult problem to solve. Also, we may be creating more contact constraints. You're going to be creating more contact constraints when you do these speculative contacts, because you're going to be adding constraints for things that are not even touching now. So that's where the cost of this algorithm is. All right, so here's another solution. The idea is to use the time of impact. So this is kind of like speculative contacts. We go to t equals 6, take a tentative time step to t equals 7, and then wrap a bounding box around that and say, did anything bad happen in between? Well, that bounding box is intersecting the plane, so I better consider a collision with that plane. So what the time of impact does is actually finds that in-between time where the ball actually hits the plane. OK? So that's just some arbitrary value in between, according to the motion. And the way it works in the simulation, then, is you just advance to that time of impact. You integrate forward to that time of impact. Apply your collision, whatever restitution or whatever scenario you have, and then take a substep to finish off the time step to t equals 7. So that's where the added cost is. It's computing that time of impact and then taking the subsequent substeps to finish off the time step. And this is the method I am going to pursue in the rest of this talk. All right, so we used a continuous collision on Diablo 3. We have a physics engine at Blizzard called Domino, and it uses this time of impact calculation, and it does this substepping. And I want to show you a couple of videos why this is really important in games. All right, so in this scenario, I've turned off continuous collision. And so here we have the female barbarian in Leia's room whacking on some zombies. Now, if you look at what the zombies are doing, you could see that they're getting stuck in the wall or going through the wall, because I had continuous collision off. I want to show that video one more time. So try to pay attention to what the zombies are doing. So that last one, it's very obvious he's hanging in the wall above. So what's happened there is those zombies are ragdolls, and they have multiple pieces. And we're just doing discrete collision detection. And discrete collision detection is kind of like rolling the dice. You know, maybe some piece of that zombie would hit the wall, but other pieces tunneled through. And so the zombie would get partway through and then get stuck in the wall. And here's what it looks like with the continuous collision detection turned on. So you can see the zombies are just hitting the wall and sliding off. That's the result you want. And here I'm only doing continuous collision detection between dynamic and static objects. For this kind of situation in Diablo, we don't care so much about dynamic versus dynamic continuous. Nevertheless, some of what I'm going to show you today could be applied to the dynamic case. So in particular, for the rest of this talk, I'm going to focus in on the time of impact problem. So we're just going to normalize that time step to be between 0 and 1. And I want to find that in-between time, alpha, where the shapes first come into contact. And I'm just going to work on the problem of convex polygons. I'm going to cover this problem in 2D, but much of the algorithm extends to 3D. And I'll talk a little bit at the end about 3D. As far as doing the substepping and handling those in-between events, I'm not going to cover that. Just the time of impact alone is a big topic, and I want to give it the attention it deserves. All right, so computing the time of impact between two shapes can be done with varying levels of accuracy and performance. So I'm going to walk you through a few different approaches to that. So one of the simplest techniques that you can do is use a raycast. So you have your initial position, your final position, fire a ray between those two positions, and see if it hits something. And this can kind of work OK in the dynamic versus static case, not really that well in the dynamic versus dynamic case. Let's just say we're just doing dynamic versus static. I fire the ray, it hits the plane, then I move the ball to where the ray hits the plane, and now I can let the collision system take over. So this kind of works, and I actually used this when I worked at Crystal Dynamics on Tomb Raider Legend. But you can run into some trouble with this algorithm. It is fast, but it is crude. If you have an oblong shape, like this box that's translating and rotating, I could fire a ray between the centroids at the first position and the final position, and then move the box to where the ray hit the plane. Well, now the box is kind of stuck into the plane. And I'm kind of crossing my fingers here, hoping that my constraint solver is going to push that box out of the plane. It might work in this case where I just have a simple plane. But with a real game geometry, you have all kinds of tessellation and all kinds of terrain features. You might actually get into a situation where it gets stuck and it just can't resolve itself. So I had that problem in Tomb Raider. So what we did is just restricted the aspect ratio of our shapes. We didn't allow the shapes to be too long and skinny. So I know that they're still using some of my code in Tomb Raider, so you might look at the latest Tomb Raider game and see if you see any long, oblong shapes moving very fast through the world. All right, so the Raycast technique is pretty crude. Can we improve the accuracy? Well, the first thought you might have is, well, let's just do a shape cast, a linear cast. So I'm just going to ignore the rotation, and I'll just do a shape cast from the initial configuration to the final configuration and find where that shape cast hits the plane. And then at the end, I still have to have rotation, so I have to apply the rotation instantly at the end. And this is kind of weird because I said I got the time of impact, but the shapes are not actually touching in this case. So this is not really an algorithm that I pursued anymore because it didn't seem like it would really work. However, linear casting is very useful for things that don't actually rotate, like character controllers, where you have like a capsule for a character that's just translating around the world. Linear casting is very useful for that. OK, so that's not working. So you could say, well, I really want something more accurate than raycasting. So what about just breaking up the shape and looking at all the features and doing a really precise time of impact for each feature? So here I could take each edge in turn and try to find the time of impact of that edge with the plane. And then I've done all these features, and I just find the one that hit first. And then that one that hit first, that's giving my time of impact. Well, this can be very accurate. You can figure out in some schemes, I'm going to interpolate the motion such that I can form some sort of polynomial or whatever and solve this problem in closed form. Or you can apply some sort of numerical root finding technique. But it doesn't really matter, because this brute force approach is just way too expensive. So for example, if I had two boxes in 3D, and I'm trying to find the time of impact between these two boxes, well, I have to sweep all edges of one box against all edges of the other box. So that's 12 times 12. Then I have to sweep all edges of one box against all the faces on the other box. And that's, again, adding up quite a bit. And I almost have to do almost 300 root finding problems. And that's just way too expensive for games. I might use this for, if I'm building a satellite or something like that, but not for games. All right, so I was really looking for something more accurate than raycasting, but not so expensive as this brute force technique. And I came across this algorithm called conservative advancement. And I thought, wow, this is really saving me. This is what I need, because it is not brute force, yet it is very accurate. So conservative advancement can find the time of impact between two moving convex polygons. So these polygons both have a linear and angular velocity. I also have some other data that I need for conservative advancement. I need a radius value for these polygons. And that radius value is the distance of the furthest point from the centroid. So I have that RA and RB there. Those are the radius values. So basically, if I had a circle centered on the centroid of that radius, the entire polygon would fit in that circle. Not a big deal. You can pre-compute that. And then I need, for conservative advancement, some way of computing the current distance between the polygons. Well, I just use GJK. So GJK is a distance algorithm. GJK stands for the authors of the algorithm, Gilbert, Johnson, and Kearthy. I covered GJK back in 2010 at the GDC. I'm not going to get into details of the algorithm. You can look at my presentation from 2010 on box2d.org. But just assume that GJK is this black box algorithm that's going to reliably compute the closest points between two convex polygons. And from that, I can get the distance. All right, so now I have all the data I need for conservative advancement. Now here's how it actually works. What I want to do is find a bound on the motion such that I can advance some amount of time and guarantee that the shapes are not going to overlap. That is kind of the fundamental statement of conservative advancement, is I want to make conservative time steps forward where I can guarantee those shapes are not going to overlap after those time steps. So what we have in this inequality on the bottom is, in this term in brackets, is kind of a velocity bound. And so you can see the first term there is saying that the relative linear velocity dotted with the unit vector along that distance vector, I'm adding that up, and then I'm going to add in a really kind of gross approximation of the angular motion. I'm just going to take the absolute values of the angular velocity, multiply those by those radius values, and then add that up. And then, so that's some sort of approach velocity, or a conservative estimate of the approach velocity of the convex polygons. And then I'll multiply that by some time step. Now, when I multiply the velocity there by a time step, that's some sort of motion. And that motion better be less than or equal to the current distance. And so this is the theory of conservative advancement, that if I take a time step that satisfies that inequality, I'll be guaranteed at the end of that time step, those shapes are not going to be overlapped. So how do I turn this into an algorithm for computing the time of impact? Well, what I'll do is I'll just go ahead and solve for that time step. So I divide the current distance by that velocity bound, and then that gives me a time step. OK, but I said that I'm guaranteed that they're going to not overlap at the end of that time step. I'm not guaranteed that they're going to actually be touching. They may not be touching, OK? But I am pushing time forward. So eventually, they should touch if I iterate. So here's how it works. I call GJK at t equals 0 to get the current distance. And then I start iterating while that distance is greater than some tolerance. So now we have a numerical algorithm. We're trying to converge within some tolerance, some small distance. And so while that absolute distance is greater than the tolerance, and the time step hasn't passed the end, I'm going to go ahead and compute that time step using that conservative advancement formula, the absolute value of the distance divided by the velocity bound. Then I'll just go ahead and advance time forward. So t equals t plus delta. Now I reposition those polygons and then compute the current distance again. And then I go check those conditions again. Am I within tolerance? Have I passed the end of the time step? OK? And if any of those conditions fail, then I'll exit the loop. And you should eventually converge, right, because you're always advancing time. Either what happens is the time hasn't reached 1, so then I did get the time of impact. Or I went past the end of the time slice, and there's no collision. This is great. I mean, this algorithm, if you have GJK, you can implement this algorithm in a day. It's very simple. And so I was really happy when I found it. And so I hooked it up, and I started using it. And then I ran into some problems. The problems are that there are some configurations and some sets of velocities that you can get between convex shapes where you can end up just taking hundreds of iterations. It's awful. And I thought I was doomed. So I was trying to figure out how can I solve this problem? What is going on? Why is it taking so many iterations? Well, I had to step back a bit. And what helped me was to think of this as a root finding problem. I have some function, the distance of time, that I'm trying to find its root. I'm trying to find the point of time between 0 and 1 where that distance is 0. Now, conceptually, that's a root finding problem, like this curve here. But in regular root finding, my function can go negative. So I can, this graph actually doesn't happen with conservative advancement. The distance actually cannot go negative. So conservative advancement is basically like root finding from one side. And I know that that is not a very healthy approach to root finding. So, okay, well, that's all well and good. But let's look at what are these scenarios that are leading to hundreds of iterations? What is the problem, the geometric problem? Okay, so consider this configuration. We'll have this triangle above the static plane. And let's just say that triangle is undergoing a pivoting motion about point P1 at the bottom there. So it's purely rotating about that point. So that means that as time goes forward, the distance d1 between that point P1 and the plane is not changing. It's constant. All right? And then what's actually going to happen is my time of impact is actually going to happen when that point P2 swings down and hits the plane. Conservative advancement doesn't know that. All it knows is the current distance and this velocity bound. All right, so if you look at this formula for the time step, that time step gets smaller as that distance d1 gets smaller. So how does that look as a root finding problem? Well, again, the distance can't actually go 0, but let's just say it can. And here's how the root finding problem looks, is the distance d is constant for quite a while as I'm moving t forward, because that bottom point is the closest point, but it's not moving. But then what happens as I move along further, that point P2 comes down below P1, and then I get a steep slope, and then I get distance going to 0. So what happens with the conservative advancement iteration is it actually just ends up ping-ponging. It thinks that, oh, okay. All right, not touching anything. So it just ping-pongs back and forth, taking iterations. And it's not really making any progress until the very end when P2 swings down below P1. So what gets even worse is if I decrease that distance, that initial distance d1 by half. So I multiply it by half. Now I'm going to double the number of conservative advancement iterations. So the number of iterations that conservative advancement is taking in this worst-case scenario can get arbitrarily bad the smaller I make d1, until d1 is below my tolerance. And keep in mind, each iteration is a call to GJK. Now, GJK is pretty quick, but it's not that quick. You don't want to be calling GJK 100 times. All right, so I knew I needed to change conservative advancement. The way it was working was running into these bottlenecks. So I enhanced conservative advancement. I changed it. And my goal was to change it so I can convert it into a standard root finding problem. I wanted to have two-sided root finding. Also, I maintain this aspect of conservative advancement, which is nice. It's working on the closest features. It's not a brute force method. Also, it is an iterative method, so it's still kind of a numerical method. You're going to have some tolerance. And one other feature is that it's tunable. So there's several components that go into bilateral advancement, and you can kind of swap them out to trade off performance versus accuracy. And we're going to cover this in detail now. So let's just start off with this simple case. I have a point under linear motion against a plane. So here's how I solve that problem. I get the parametric line formula, and then I have my plane equation. So I have the normal for the plane and the offset W. Okay, so those are the two things I'm starting with. I substitute the line formula into the plane equation, and then I can solve for t. Now, in the case where the denominator would be 0, that means that the line is parallel to the plane. So in that case, I'm just going to say there's no time of impact. All right, so unfortunately, it's never this easy. So let's start to look at more and more complex problems. So what if that point is now on a moving frame? That frame could be translating and rotating. All right, so I could try to come up with some analytic formula like I just did with the line. And maybe I could get that working in this case. But we're going to be adding more complexity later on. We may have two moving shapes. We're going to go into 3D later. And so I pretty much abandoned the analytic approach at this stage and said, OK, I'm going to do numerical root finding. And here's how I'm going to set it up. Is I need to find some function that I can do root finding on. Well, I already had this notion of, OK, I'm going to substitute the line formula into the plane equation. So I'll do that, and I'm going to now evaluate the error in that plane equation. And that's the separation value. So the awesome thing about this is this separation value can be positive or negative. Now, how do I actually compute this? Well, it's basically that point is on this moving frame, and just say I have some way of interpolating the motion in that frame. I'm interpolating the rotation and the translation, and then so at any point of time t, I can compute the world position of point P. And so I can then evaluate that separation function. This separation function is really the heart of the bilateral advancement algorithm. So notice that the separation is positive at t equals 0. So this is kind of the root finding curve that goes along with that picture from the previous slide. And then at t equals 1, the separation is negative. Well, I know if I have a continuous function that goes from positive to negative, there must be a root in between there. It must be crossing the t-axis. All right, so I can now apply any standard root finding technique. Easiest one to get started with is, I'll cover that in just a second. So one more key point is that I need to, for many root finding algorithms, it's good if you bracket the root. So that's essentially the situation I have here is that I know that I have one value at t equals 0, which is positive, and another value at t equals 1, which is negative. And I also know, the range is from 0 to 1. So I know the root is somewhere in that range. So this is an invariant that I want to maintain while I'm doing root finding. OK, so one of the simplest algorithms that you could do for root finding is called bisection. And it works on that invariant. And here's how it works. So I have this table here, and I'm going to set up iteration 1. And that starts with my initial bracket. From t1 is 0 to t2 is 1, all right? And I know that at t1, the separation value is positive, and at t2, the separation value is negative. And then how I proceed is I divide that domain in two. So I go to 0.5, then I compute the separation value at 0.5. And this figure, obviously the separation value at 0.5 is positive. That means I can push t1 forward. So I reduce the bracket size in half, and I'm maintaining the same invariance. And I can just continue on. I'll divide that bracket in half. The halfway point between 0.5 and 1 is 0.75. I evaluate the separation function there. I find that's still positive, so I can move t1 forward a bit more. And then the halfway point there is now 0.875. I evaluate the separation function. Oh, it's negative. That means I'm going to push t2 back. All right, so that bracket is shrinking. I'm making steady progress here. And this is a numerical algorithm, so I'm just going to keep iterating until that separation value is small. It's never going to get exactly 0 unless you're incredibly lucky. So The nice thing about bisection is it's always making progress. It's always dividing the domain in half. All right, so I like that bisection is very reliable, but I also know from many, I actually drew a lot of these graphs of these separation values for real problems, and I found often they're very linear. So I said, well, maybe there's an algorithm that works even better for the linear case. And so the false position method actually works quite well in the linear case. This curve obviously is not very linear, but I'm going to show you nevertheless how the algorithm works. So we start out the same way as bisection. We have our initial bracket. And instead of dividing the domain in two, I draw a line from the initial point, from the T1 point to the T2 point, and find out where that line intersects the t-axis. So that's just a very simple calculation. And I don't know what that value is in this picture. I'm just going to call it U2. But nevertheless, at U2, I can evaluate the current separation. Remember, I'm just interpolating. I'm just interpolating the orientation translation of the object. So each of these evaluations is cheap. OK, so in this case, I find out, oh, the separation at U2 is positive. So again, I'm just going to push T1 forward, find that T intersect again by drawing a line from the T1 point to the T2 point. And I find, oh, the separation value is still positive, and I keep moving T1 forward. And that's kind of how it proceeds. So I found, just through trial and error, that the false position method worked really well when the function was close to linear, but sometimes it wasn't, and false position wasn't converging as quickly as I had hoped. So I thought, well, just to be safe, I'm going to mix in some bisection. And so how can I do that? Well, what I actually ended up doing is I would do one bisection step, and then I would do a false position step, and then back and forth. So how can I do that? Well, the reason I can do that is because both algorithms are maintaining the same invariant. And this is not anything crazy new. There's all kinds of root-finding algorithms out there, and they do combine different methods. And this may not be the best root-finding algorithm for this problem, but just as it turns out, I got to this stage, and then everything just worked. And so I never really looked back. But maybe you can find something better. Anyway, yeah, it just keeps iterating. I have some maximum number of iterations. I will bail out the algorithm, so I'm not spinning forever if something goes wrong. But normally what happens is the separation value gets less than some tolerance, and then I just terminate. All right, so now we know how to do the point on the moving frame versus this static plane. What would happen if I now allow that plane to move? So now it's a dynamic versus dynamic case. Well, I can apply interpolation to compute that normal and that offset as a function of time. All right, so it's just the plane is now its own moving frame, and I interpolate that frame, and I compute the normal in that frame and the offset, and that's fine. So I can do that, and my separation function actually is still working. If you look at t equals 0, the separation is positive, and t equals 1, the separation is negative, and it's just the same root finding problem. It's just now that the function is a lot more complicated. Fortunately, those root finding algorithms like bisection and false position method, they don't care how complicated that formula is. You just need to be able to compute it on demand. And so this problem is not a problem at all for what I've shown you. You can just do it. All right, so let's get to the next level of complexity. I want to do a polygon, entire polygon versus a plane. So here I'm just going to show a triangle as an example. And it has to be a convex polygon. So what I'm going to do is I'm just going to consider the vertices of this polygon, because I have an infinite plane. So that's going to work. So what I can do is just compute the time of impact for each point to the plane, and then take the smallest one. And then that would be the time of impact for the polygon. All right, but we can do better than that, actually, because that's almost kind of getting back to a brute force thing. So instead, what I do is I move the entire polygon to t=1, and then look for the deepest point, which point has the most negative separation value. This is basically just a support point. I'm going to compute the furthest direction in the negative normal direction, or the furthest point in the negative normal direction. And that turns out, in this case, is point P2. So I find that deepest point, then I say, OK, I'm going to compute the time of impact for that deepest point. And so that's going to push the whole polygon back up. So I find that time alpha, I push the whole polygon back up. In this case, the whole polygon is clear, and I do have the time of impact. You might have a case, though, where there's some stragglers. There's still some points below the plane. OK, that's not a problem. I would then go again and find the deepest point, and then solve for the time of impact on that reduced domain. It's going to be between 0 and alpha now, instead of between 0 and 1. And you can just keep doing that. Keep pushing the deepest point back until you have clearance. Most of the time, it's actually just 1 point. All right. You may have noticed we actually missed something. I said, look at the separation value at t=0 and the separation at t=1. If those are both positive, the algorithm would just bail out. But you might actually miss something that happened in between. You could have a function with multiple roots, like this figure over here on the right. And so I actually missed that in-between collision. Is that a problem? Well, it's actually, in many cases, not a problem at all. What we're getting here is some sort of rotational tunneling. That's what's generating multiple roots. You're not going to get multiple roots with just pure translation, but you can get it with rotation. And so what you're going to have happen is some cases, something will rotate in, but then at the end of the time step, it had rotated back out. For the kind of games I worked on lately, this doesn't matter at all. I just want to keep things from falling out of the world in most cases. This does not have that problem. The objects are not exchanging sides. It's just kind of passing through each other and then passing back out. Now, that doesn't mean I'm going to miss all rotational collisions. Obviously, there may not be 2 roots in that domain, and I'm not going to miss it. So I'm still handling rotation. It's just sometimes there's going to be some sort of fast rotation that I might miss. Now here's where the tunability part comes in. If you want to find those multiple roots, you could do that. You could change the root finder and look for those multiple roots. That's much more expensive, so I don't do that. But you could change the algorithm to do that if you wanted. All right, so let's get to the final problem, computing the time of impact between 2 convex polygons. So the setup is similar to what I showed you before for conservative advancement. Instead of computing the distance, what I'm going to do is modify GJK slightly to return the closest features. So the closest features are the lower vertex of B and that upper edge of A. Okay. All right, so how is that useful? Well, what I'm going to do is I'm just going to extend an infinite plane along that upper edge of A. All right, A can still be moving. If that's fine. It could be a completely dynamic versus dynamic case. And I'm just going to go ahead and compute the time of impact now between that polygon B and that infinite plane there on the top of A. Here's where convexity is really helping me, because I know that everything on A is below that plane. Also, I'm just going to forget about that lower vertex of B. It doesn't matter now. I'm just going to consider all the points of B. All right, so I can compute the time of impact now, because now it's just polygon versus plane. I already showed how to do that. All right, in this case, the time of impact with that plane is actually the time of impact between the 2 polygons. So this worked out. But you can imagine a situation where it's not really working out. You actually have a time of impact on the plane, but that part of the plane is not a part of A. All right, so that seems kind of like this ghost collision problem. Well, it's OK. We can deal with this. So just go ahead and move B to that time of impact, alpha 1. That's now a tentative time of impact. And then call GJK again and get the closest features again, and also compute the current distance. If that current distance is not within tolerance, I'm just going to use these new closest features and repeat the algorithm. So now I have that bottom edge of B is now my infinite plane, and I'm going to collide the whole polygon A against that infinite plane. And that gives me, I'm advancing time even further now. And in this case, I found the true time of impact. All right, but there's one more consideration, is what if the closest features are actually 2 vertices? So how could I handle that? Well, you could look for a nearby face and then draw an infinite plane through that. If that's separating, that might work. I chose not to do that. What I do is form a unit vector that points from one vertex to the other. So in this case, U points from A to B. And this is the t equals 0 configuration. Now, nothing says that these 2 polygons are approaching, that their vertices are going to collide or anything. This is just an intermediate configuration. They may actually rotate like that. So you can see A is kind of sliding down, and B is kind of spinning over. And so that's the t equals 1 configuration that you might have. Well, that's fine. So what I need to do now is figure out how to build this separation function that I can feed into my root finder. And here's how I'm going to do it. I'll find the support point on B in the negative U direction and the support point on A in the positive U direction. And I'll remember those points. And those are now the deepest points. I have 2 deepest points instead of 1. All right? So I have those. I'm going to store those points in local space so that I can recompute them at any point in time. And I'm going to stick them into this separation function now. So now I have a different separation function. But it's fine. The root finder doesn't care about this. It just has a function that's trying to find the root on. And my root is bracketed. I have that same behavior where the separation goes from positive to negative. And then when I feed this into the root finder and solve for the root, what I end up is like a configuration like this, where the polygons are separated by a plane that is parallel or perpendicular to that axis. All right, so yeah, clearly in this case, those vertices did not collide. And now I'm in a configuration, OK, they're not actually quite touching. But what I'm going to do is just recompute the closest features. Clearly, in this case, it's going to be this vertex of A is going to be closest to this close edge on B. And so I'm just going to advance to the next set of features until I get the time of impact. So that's it. That's pretty much the gist of the algorithm. So here's kind of the flow chart for this algorithm. You don't have to learn this all in detail right now. I just want to point out a few key points. There's 3 levels to the algorithm. At the innermost part, I have this purple box with this root finder in there. Okay? And that root finder is taking a separation function. And then around that, I have this deepest point solver that's progressively pushing out those deepest points until I have clearance for the current feature pair. And then on the outer loop, I have the feature advancement. The outer loop is the expensive part, because that's where I'm calling GJK. The inner loop is just interpolation and support points. So it's pretty simple. All right, so you probably wonder, how does this perform? Can I really use this in games? So I'm going to show a quick demo of Box2D. All right, so So here's a demo of this long skinny box falling down onto static configuration, and I have continuous collision turned off. And you're seeing some artifacts there and some tunneling. So obviously, this demo has some problems without continuous. So I'll turn on continuous, and you see a much nicer result. And you can also see the timings up there. I don't have too much time to go deep and deep details, but you can see the number of GGK iterations. It's always 4 or less. There's not too many root finding iterations. And the whole thing is almost always under about 10 microseconds. And this is kind of a wimpy laptop. All right. Let's get back. So like I said, you can apply this to 3D. This is the domino test bed. It looks suspiciously like the Box 2D test bed. But we can do 3D. And yeah, it works. It's more expensive, obviously. You also, I showed you 2 separation functions, one for point versus plane and one for vertex versus vertex. In 3D, you also have to do edge versus edge. And that kind of chimes in with what Dirk was talking about earlier with needing to consider edge versus edge in 3D. All right, so here's references. I did a lot of research working on this project, and I hope you find these references useful. And you can reach me at box2d.org. I'll have this presentation up there. You can ask questions. You can also reach me on Twitter. And that is the end of my presentation. Thank you. And I'm happy to answer any of your questions. I have a few minutes here. Yeah, and if you wouldn't mind coming up to the mic, that will help a lot.
I was wondering how many of the issues you realized on pen and paper and how many of them you had to calculate to realize when it was going wrong.
Right, so the question is, how many of these issues did I figure out with pen and paper, and how many did I have to actually start computing things? So yeah, a lot like conservative advancement, I didn't find out the issues until I actually hooked it up in my engine and started running it, and then just ran into these bad situations. So in my initial trials, like some very toy problems, it seemed to work great. So yeah, a lot of this stuff, just you don't really figure it out until you really try it and test all sorts of situations. Yeah. So experience matters.
For the case of multiple roots, if you were concerned about like handling that, is there a way? Is that easy to detect that there's multiple roots? Or?
So how would you handle multiple roots? Well, I really push you back to the root finding literature back there, because at that level, it's really just a root finding problem. Unfortunately, you don't have a nice polynomial, so you're going to have to do some sort of global search, I think, through that domain. You're probably going to, what I imagine you would do is divide your timescale up to some value that you consider acceptable, and then start sampling the function in there. So you probably have to do some sort of exhaustive search, yeah.
All right, thanks.
Yes?
Does the algorithm that you mentioned today, do they apply for a specific set of problems within collision detection, or do they replace just traditional volumes and interaction between bounding volumes? Meaning, is this specific for fast-moving objects colliding with others, or?
Oh, I see. So could this be applied in other situations? I've really only applied this to solve the problem of tunneling. I have used this problem, or this technique, to also handle some fast-moving objects versus other moving objects, and it works okay in that case. The real difficulty comes down to resolution, and how do you handle all this substepping and keep that having reasonable performance. You might be able to use, you can actually, I use the same algorithm for linear casting. I don't have an optimized linear casting. So you could use this for a character controller as well, and we do that. So
thank you.
Sure.
I'm a little bit curious about how much you're using this in game scenarios. how much entities you're actually comparing in real-life games, and how expensive in those contexts you find this part of the whole physics simulation to be.
Right. So how expensive is this in real games? So if you look at Diablo 3 and you start looking at the profile, you'll find that if you have a situation where like a whole bunch of stuff flies up in the air and then all slams down at once, you're going to get a bit of a spike to handle all those simultaneous time of impact events. Normally, though, they're not all happening in the same frame. Another thing is if objects are just kind of resting on each other, not having a really super high relative velocity, you can basically do some sort of cheap conservative advancement type of check and say, well, given the relative velocities of these shapes, there's really not any concern that they're going to tunnel through each other, so I'm not even going to do the time of impact. So there's lots of intelligent things you can do to not be calling this thing all the time. So does that answer your question?
I think partially, but you didn't find this to be an issue or concern regarding overall performance of the physics?
Once I got to bilateral advancement, the serious performance issues went away. So if you just have a bunch of objects like ragdolls sliding around, like the scene I showed you, you're going to get maybe 1 or 2 frames where it's doing that, but it's actually, let's say they're all doing that, and you're doing discrete collision, and you're doing your constraint solving. And what I found, if that's all happening about the same frame, they're each about 1/3 of the frame. Yeah.
Thanks.
Any more?
Just kind of an extension of that. Is there any kind of scene solver that you would go to implement to figure out if you're going to hit those high impact situations? Is it worthwhile, or are they so much of an edge case that it's not too much of an issue?
So is the question, how do I handle finding which shapes might hit with each other?
Basically taking what you just did there on a per object basis and now essentially applying that to your entire scene.
Okay, so yeah. So how do I apply this to an entire scene? So first of all, what you saw there in the Diablo demo, that room is a simplified triangle mesh. And when you're performing the time of impact, you're basically, like I showed before, we're going to wrap a bounding box across the swept shape. And then I will intersect that bounding box with the triangle mesh, find the triangles that intersect that bounding box. Mm-hmm. I know the triangles are not moving. And then I will have to perform a time of impact with each triangle. So yeah, you want to simplify your collision if you're going to do this. Okay. And our collision is greatly simplified from what you see visually.
I guess is there some kind of pre-compute step that you look at your entire scene and go, I'm going to need to test these in the next coming frame?
Yes. So how do I know what I'm going to need to test? Is I actually, for each AABB that overlaps in the broad phase, mm-hmm. I keep a data structure called a contact or an arbiter or an agent, whatever you want to call it. And basically, you have to classify each of those agents. Is this thing fast? Do I need to do anything with that? Another way to do it, this is kind of an open question for me, actually. Another way to do it is try to feed off of your island solver. If you have an island solver, that after you do your discrete simulation on an island, then, okay, now let's take that island and let's go worry about any time of impact events for that island. Yeah.
Thanks.
Sure. All right, we better move over to Gino now. Thanks, everyone.